Ladies and gentlemen, welcome to my brand new science channel. My name is Christoph Grübe and I am a science journalist, and on this channel I will talk about the most fascinating things in maths, physics and engineering. To start things off, let's talk about one of my absolute favorite topics that in fact connects all of these subjects: quantum computing. The idea of a quantum computer goes back to a lecture on simulating nature with computers, given by the famous physicist Richard Feynman in 1981. In this lecture, Feynman put it in very memorable words. He said, nature isn't classical, damn it, and if you want to make a simulation of nature, you would better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy. Well, how right he was. So, Feynman suggested to use a quantum computer to simulate nature. Today we call this task a quantum simulation. But why can't a classical computer do that? Why do we want to use a quantum one? Well, fact is that nature works according to quantum mechanics, a very strange theory of physics. The smallest amount of information in quantum mechanics is a qubit. In contrast to a classical bit, which can either be 0 or 1, a qubit can be in a superposition of 0 and 1, which is kind of something in between. You can localize a superposition on the blosphere, where the poles are 0 and 1. The state of such a qubit can be represented as a two-dimensional vector, where the components alpha and beta are complex numbers that we call probability amplitudes. Because if we measure the state of the qubit, we can calculate the probability to get 1 or 0 by taking the absolute squares. The important thing is now to keep track of the state of a single qubit on a classical computer. We have to store information about two amplitudes. To do that, we need a certain amount of classical bits for each amplitude, depending on the amount of accuracy we want. And here comes the problem. If we add another qubit, then the state vector of the two-qubit system has 4 components. If we add another one, we get 8, and so on. You get the idea. If we only wanted to simulate the small number of 300 qubits on a classical computer, we would need to keep track of 10 to the 90 amplitudes, which is already more than the number of atoms in the observable universe. So, for a classical computer, the task of simulating nature is not impossible in principle, but in practice the calculations are exponentially complex, so that we cannot execute them anymore on any hardware in, say, the lifetime of the universe. The mathematical discipline that investigates this problem is called computational complexity theory, and one of its major results is that problems with exponential complexity are hard to solve and anything below is easy. And that is where a quantum computer has the chance to outperform the classical one, a possible speed up of calculations. This is called quantum supremacy. But don't celebrate too soon. There are 2 incredible hard problems that lie at the heart of quantum computing. The first one is to even find tasks that are hard to do on a classical computer and easy on a quantum computer. In fact, we have only found 2 quantum killer apps up until today, called Grover's search algorithm and the quantum Fourier transform, which we can use, for example, to speed up optimization problems and break RSA cryptography. The second problem is to actually build a quantum computer. For any relevant task, what we need is maybe around 1 million logical qubits, which are qubits with quantum error correction. To achieve that, we would need probably 1 billion physical ones. Well, what we have today is around 50 physical qubits, despite the billions of dollars invested every year in the field by many governments and tech giants. Even a few Nobel Prizes have been earned by researchers that work directly or indirectly on quantum computing, through their work on superconductors, trapped ions and topological qubits. So, Richard Feynman said, it is a wonderful problem, because it doesn't look so easy. And in my opinion, he was right. That is what makes it exciting. What do you think? When will we have quantum supremacy? Write it down in the comments. Thanks for watching, and if you enjoyed the video, leave a like and subscribe to the channel. See you next time.